Let's now begin Chapter 8. In Chapter 8, we'll talk about various applications of aqueous equilibria. So this is going to connect a lot of the concepts that you've learned in Chapter 6 and Chapter 7, and you're going to use what you learned in those chapters towards solving new problems that have very important applications in real life. In this first section of Chapter 8, we'll talk about what a buffer solution is and talk about the common ion effect and its role in predicting the pH of a buffer. So what's a buffer solution? A buffer solution is a solution that is capable of resisting large changes in pH upon the addition of small amounts of strong acid or strong base. This is so important in so many different living systems. This has so many important applications in biology, in marine science, and in a whole range of other fields. For example, human blood is a buffered solution. Human blood is buffered at a pH of about 7.4. And that is a really important thing because the enzymes that control a lot of the chemical reactions that happen in our bodies are only effective within a small range of pHs. So if your blood pH goes too far away from 7.4, you may not be able to have the enzymes in your body perform the reactions that are needed to keep you alive, and then it's like game over for you. The reason why our blood needs to be buffered is because on a day-to-day basis, we eat and drink food and liquids that have a whole range of pHs. For instance, if you drink soda that is acidified with carbonic acid, citric acid, some other acids, and so sometimes some sodas have pHs of like maybe 1 or 2. And if you were to drink the soda and then that soda, gets absorbed and it hits your bloodstream, if your blood were not buffered, that would drive the pH of your blood way down and then it would be lights out for you. But it's because of the fact that your blood is a buffered solution that you're capable of absorbing that acid that you put into your body, and you don't have to worry about it. Additionally, a lot of medicines are also only effective in small ranges of pHs, and so it's important for your body to be, buffered at a specific pH to make medications effective for you. Another example of a buffer solution would be ocean water near the surface. This is a buffered system at a pH between, let's say, 8.1 to 8.3, and having a buffered solution at about that pH window is crucial for marine life that you'll have in the ocean. If the pH were to deviate significantly from that, you would run the risk of killing a lot of marine life. If the ocean were to get too acidified, that could dissolve the exoskeletons of a lot of marine life and would be very bad news for them. So it's very fortunate that the ocean is buffered to try to make the ecosystem a little bit more resilient. Now, what do you need to have a buffer? In order to have a buffer, you must have both a weak acid as well as its conjugate base. So for example, if you had a solution that contained HCN and also the salt NaCN, this would be a buffered solution because you have the weak acid, hydrocyanic acid, and you also have the conjugate base from the cyanide ion that comes from NaCN. So this solution contains both, therefore this solution would be a buffer. We'll talk about the role that each of these components plays in maintaining the buffer and in resisting the pH as we go through these presentations in this section. When we start making a buffer by taking a weak acid and then adding some of the salt of its conjugate base to it, we have to think about something called the common ion effect and what role that might play in the pH of our system. So we're going to consider a solution of hydrofluoric acid that has a pH of 1.6. And now I want to make this solution a buffer by adding sodium fluoride, so that introduces the fluoride ion. I want you to think about what that would do to the pH of the solution. Would it maintain the pH at 1.6? Would the pH go below 1.6, or would the pH rise above 1.6? Take a moment to think about this and put in your answer on the other side of the question. We'll go over it together. All right, so let's go over the answer to this together. I'll remind you that when we're talking about making predictions of pHs, it's beneficial to consider what you have in your solution and what chemical reactions are occurring. So let's think about what we have when we just have the aqueous solution of HF. If we have just HF, then the HF would dissociate in water, at equilibrium to make H plus and F minus, right? And it's equilibrium because HF is a weak acid. So let's write that reaction out. HF dissociates at equilibrium to H plus F minus. This is the reaction that controls the pH of the solution. Now, what I'm going to do is add sodium fluoride. Sodium fluoride is a soluble ionic compound. So sodium fluoride breaks up completely into Na plus and F minus. And so adding NaF raises the concentration of the F minus ion. This is going to put a stress on the system. And now we can use Le Chatelier's principle to predict how that will affect the equilibrium of this reaction. So adding NaF increases the amount of F minus ion. By putting that stress on the system, Le Chatelier's principle says that the reaction has to react in a way to counterbalance that. You have to have this reaction shift to the left to get rid of that excess of F minus ion that you now have. Now, as the reaction shifts to the left, you're shifting away from H plus. So you're going to be decreasing the concentration of H plus ion in your solution. As a result, the solution will be less acidic. Because the solution is less acidic, you will see a rise in the pH. pH rises, and so we're going to say that the pH of this buffered solution is going to be higher than 1.6. Another way to think about it is when you added NaF to the solution, you added effectively a weak base. So if you added a weak base, you've made the solution a little bit more basic, you've raised the pH. It's just another way to think about it that doesn't involve Le Chatelier's principle. That brings us to the end of this first video of Chapter 8. Next, we'll talk about how we would actually calculate the pH of this buffered solution.